say.
It's all right.
Don't worry about the meters.
Who's got He's got one.
It can be qualitative, which means that the marks don't matter. All right, guys. So here's the example we should be working on right now. Yes. Okay. Hopefully we have a couple lines around at this point. I'm going to come around with the iPad and take some pictures of some of your guys' graphs here in a little bit. So,
Please don't take a picture of mine.
My graph.
or mine.
I need some help. I don't have no notes. I don't have no notes yet.
All right. Does anybody have a picture they want to share with their classmates?
Oh, that's a nice branch.
What is that? Is that you? Okay.
You're in the way.
Can you put that on me? Put it on me.
Branch, you're in the way.
You see Kyle?
You're in the way.
Put me on there.
Branch, you're in the way.
I know. Scott, it's been up there for like 5 minutes at this point. You should already have your graph drawn. Okay, guys, if you don't have a graph drawn, it's because you sat there and did nothing for the last 5 minutes.
Mr. Brent,
All right.
I haven't been here.
Does everyone want to share their graph?
Why are you recording?
Because gives us something to talk about. Can you look at yours one?
Why you
Okay.
got shoe on
So
there?
guys, here is Juan's graph. Okay.
Good job, Juan.
Juan, you want to explain to us what's happening here? Which one's the red line? That one. Okay, which one's the blue one? Okay. So I said the blue one after a certain amount of time starts to decrease speed, right? How's that shown in your graph? Okay. So the speed going from having slope to being no slope, that's the decrease in speed? Yeah. Okay. Is Juan's decreasing speed over time, or is it kind of like an instantaneous decrease? Okay. Thank you, Juan. Anyone else want to share?
No.
No?
It's you.
Anyone else?
Yeah, I do.
Katrina, your graph is very nice. I'd like to show everybody if I can.
Yeah.
No? Whitney? You want to share, Jameer?
No.
Oh, come on now.
Can I show you mine?
It's just
Yes.
recording randomly.
I am just recording carpet in my shoes right now.
Yeah, put mine up there.
Ah.
Low first.
All right, so here we
You
go.
have like nothing on there.
Here's another one. How's this different than Juan's?
It has a curve in the line.
There's a curve? Kind of curved, right? We have a steep slope,
Straight lines.
and then a less steep slope. Can't find my finger. Right there, a less steep slope right there, right? Right? And then what's the horizontal line mean? It died. It's not moving anymore, right?
Yeah.
So Katrina and Juan both agree with the steep slope to start and the horizontal line to end. They differ, right, kind of where that red line is, right?
Yeah.
Right? So at that moment, that is where the speed is decreasing. Okay. Thank you, Katrina. Anyone else want to share? No? Lau, you're still drawing?
I did the wrong one.
You did the wrong one? No one else wants to share?
I got you.
I'm here, does.
I'm here.
Kyle, this year's.
I just made mine.
Am I this year's?
Oh, Lord.
Come on now.
That's for Omar.
Omar's? Okay. All right, here's Omar's.
Oh, you can take
Okay.
stuff like that.
How's Omar's different from Katrina and Juan's? Sorry, Juan, I'm standing right in front of you.
It doesn't.
Is it sketched?
Yeah.
How is his different than Katrina's?
Why yours curved?
Because it doesn't have decrease.
Kyle, what'd you say?
Why is this red one curved like that? Like,
It sounds wrong with. Oh, okay.
that was my fault.
That's his fault. But the blue one is curved, right?
Yeah.
but I
So
thought it's
Katrina kind of had a steep slope, a less steep slope, and then no more slope. Juan had steep slope and no slope. Omar has a curved slope,
Yes.
right? So which one shows a gradual decrease? Katrina, Juan's, or Omar's?
Omar.
Omar. Now, do you think the tumble buggy in the example? Thank you, Omar. Think the tumble buggy in the example. I think it's going to have just an all of a sudden instantaneous stop,
Yeah.
or is it going to have a kind of a gradual decrease?
Gradual decrease.
It's going to be a gradual decrease. Sorry for those of you following at home.
I thought you were going to show mine.
Oh, sorry, Kyle.
Yeah, I don't
Where
think
else
anyone's
go?
gonna watch.
Whoa!
else
People
go?
watch these.
Like 3 people.
Kyle, The one thing about yours, is the blue one going faster than the red one to start?
No.
Yeah.
Yeah, they're going like the same speed.
Their slopes are parallel, they're going the same speed, aren't they?
Mhm.
So the blue one's going twice as fast. But I do like your curve, nice job.
Thanks.
So, should the line be curved, or should it be like just a drop, or should it be a gradual?
Gradual.
Because the batteries are dying. But
Okay.
they're just straight up die.
Good, the batteries are dying, so the line should be curvy.
Mine's curly.
Ashley, try not to knock the camera. If you do, grab it real quick. Think you can do that? Alright, so if I were to draw a graph, should I draw one like Juan's, Katrina's, or Omar's?
Okay.
Omar's?
Do mine.
So, but both of you,
That's an option.
you all agreed that the red car looked like that, right? Okay, it has a constant slope because its speed is, or sorry, because its velocity. Kyle, Imani.
Sorry.
Okay, had a constant slope because the velocity is constant. Now the blue car starts out faster, right?
Oh, you gotta go up.
So should the slope be steeper or less steep?
Steeper.
Steeper. Okay. So it starts out faster, then what happens?
It goes
Slow curves.
Okay. It starts to lose battery, and what happens to the speed?
gradually.
Gradually slows down until what?
Until it just dies.
Oh, just stop.
You trying to make it perfect?
It's like the little heartbeat when it's like.
So, then the light on here. That's where they cross. Right. So this looks a lot like Omar's graph, doesn't it?
So put an extra
Is that
batteries
one?
in it, whatever you did.
I made it so that I took the diode out that keeps track of the current. So just let all the current go.
Do you have to label the graph or
What?
on the side?
I would.
You would?
Yeah. So here's the blue. Okay. I didn't really do this, Katrina.
Well, that'd be a waste.
It would be, because I'd probably break the couple of legs. Alright, Jimmy, you okay? Alright, so the biggest disagreement we had in the three graphs you looked at was in between this spot and this spot. And I know the graphs might not have been the same time period, but one of us had a straight line here, right? One of us had just an abrupt stop and then a straight a no slope, and one of us had a curved line. You guys also the curved line is the way to go. Okay. So, what's happening between these two black marks? Raise your hand if you know. What's happening to the
It's
velocity?
decreasing.
Slowing down.
How do you know it's slowing down?
Covering
The slope is not as steep, but this slope isn't as steep. Does that mean it's slowing down?
No, it's going constant.
But that one's. That one's.
Got some sound effects too. I like that. Battery dying noises. Okay. So what's happening here? What's happening?
It's slowing down.
How do you know it's slowing down?
Because
Because of what?
the slope is decreasing.
The slope is decreasing. Right? So the slope's decreasing, and that's how we know this object is
Slowing down.
slowing down. Because on this graph, what does slope represent? Danielle, what is this on this graph? What does slope represent? Nope. Close though. Velocity, because it has a sign, doesn't it? If it was speed, we wouldn't worry about positive and negative direction, but we do, right? Because we have vectors up here, we worry about positive and negative direction. So the slope on here is the velocity. So this spot, we know the slope is decreasing, the slope is changing, right? And since the slope is changing, that means the velocity is changing. Okay, Kyle.
Can you show us an example of like one that's like gaining speed?
When it's gaining speed? Well, let's think about it. Let's say the blue buggy, instead of starting out fast, it ends fast.
Yeah.
Okay? So here we have a slow speed, right? And now if I want to gain speed, what's it going to look like?
Is it gonna curve upwards or
So does the line get more steep or less steep?
more slower?
More steep. Okay? The line can get more steep. Okay? And that's got it. Thank you. And this right here is doing what, Kyle? Gaining speed. Because what's happening to our slope?
It's getting steeper.
It's getting steeper.
Then it ends fast, right?
What?
It ends fast.
So like we could have it. Now we could have a constant speed from there on out. Okay. So from here until here, the slope is changing, right?
Yeah.
So our velocity is increasing. Okay. I'm gonna draw two more for you guys. Please stop saying that. So, I have two lines up there. A black line and a blue line. Right, you guys see that? Okay. No? Right. Now, that is still a position versus time graph, so I don't label my axes. Still a position versus time graph. So, guys, the question is, which one is increasing velocity, and which one is decreasing velocity? Don't shout it out. Okay? Just want you to think. Now, if you can't, I'll label them as 1 and 2, so for our time between the blue and the black. Okay. So, Kyle. Okay. So we'll call the top one 1, the bottom one 2. Okay. Which one is increasing velocity, and which one is decreasing velocity? Oh, number 2 is the same as one we already looked at. Oh, I almost fell down.
What happened like that?
Jimmy, you'd be happy if I fell down?
I would.
Thanks, Kyle.
Should've got it on camera.
There we go. Okay.
Make them all run more.
So there's 1 and 2. I make them run enough already. All right. So there's 1 and 2. So the question is, which one is gaining velocity? Which one's losing velocity?
2.
Okay. Who's gaining velocity? 1 or 2?
1.
1 gaining velocity, says Kevin.
Neither.
Okay.
Aren't they
So
both?
then Kevin, what's happening at 2?
It's decreasing.
Decreasing. Katrina, what'd you say?
Even if you go negative, but like you're going from positive to negative, you still gain velocity.
So we're still moving faster, right? Okay. So maybe that's
Just
another
in a
question.
different direction.
Which one is just a different? Perfect. So even though we're going negative, we can still gain speed, right? Okay. So which one's going faster at the end? 1 or 2? 2?
Yeah.
Michael, you paying attention or what? Okay. So we said some people say 2 is going faster. Do you guys over here agree with that?
Yes.
Yeah. Okay. Now, have you guys learned about tangent lines yet?
No.
No one's learned about tangent lines.
No.
Anybody learned about derivatives yet?
No.
Okay. Well, the derivative of a function. If you're taking pre-calc, you'll get to it. You also get the tangent lines. If you take the derivative of a function, so it's a simple process in calculus, and I will not teach you how to do it right now. Now taking me a little longer than the time I've allowed for this. But a derivative, guys, if I find the derivative of a function at a specific time, then that derivative tells me the slope of the graph at that moment. Okay? So let's say here's my initial time. T initial. Okay? We'll draw this line up right here. Okay. Now, if I'm going to find the derivative of these two functions at that moment, it tells me the instantaneous slope at that time. So for this first one, for number 1, the slope at this moment looks like that. Does that make sense? You guys see that? So that's the derivative of the function at that moment, that slope right there. Okay? The slope of this one is like that. It's almost stationary. Does that make sense, guys? You guys see how I got the green lines?
Kind of.
Okay. Yeah. I drew a line parallel to the line at that instant. Okay, do you see it? It's called a tangent line. At the moment I drew the line, it's parallel to the black graph and the blue graph at that very moment. Okay? All right. Now if I go to my final time, we'll say final time right here. There's the tangent line or the derivative again. Tangent line. Now, for graph number 1, what happens to slope? Does it get more or less? Less. So is it speeding up or slowing down? Slowing down. We know because the slope is less steep. Okay. The blue line. Okay. The blue line, number 2. Is it speeding up or slowing down? Speeding up. Right? Because the slope goes from not very steep to more steep, right? Okay. The top one, we could say it has an increasing or decreasing velocity. What do you guys think? Decreasing velocity, right? The bottom one, we would say it has a increasing velocity. Now, if I take this from a math perspective, okay? If I take this from a math perspective, if I have a negative slope, that means my slope is... If I have a negative slope, that means my slope is increasing or decreasing slope? A decreasing slope, right? You guys ever hear that term before?
Yeah.
Yeah. Well, the person that wrote that math book didn't think too much about physics. Rex, if you draw one again, I'll take it again. Okay, just waste your graph paper. All right. So, person who wrote that math book wasn't thinking about physics too much. Because here, this slope is said to be decreasing, or it's becoming more negative, right? But the speed is actually increasing, okay? Because if this is my position axis, as graph 2 goes on, it covers more distance per unit time. So the speed increases, right? Graph 1 covers less distance per unit time, right? Does that make sense? Okay. So are there any questions about what we have there? Now, every graph I've drawn up there except for, and some of you drawn some of them too, every graph up there except for the red graph. What do they all have in common? They curve. What does that curve mean? What changes? What increases and decreases? Speed, more importantly, not just speed, but velocity. So every graph up here has a changing velocity. What's a changing velocity called? Acceleration. Pulling out the big word already, man.
Oh, yeah.
That's a big word.
It is a big word for me. I mean, it's got like 7 letters in it, and I can spell it. It's even better.
Spell it right. Oh, there it is.
I don't spell acceleration every day.
That's 12.
All right. So acceleration. Based on our graphs, does anyone know what acceleration is? Change in velocity.
Positive change.
I did not say that.
She said that.
Non said that?
Positive change.
She said-
Like,
So what is
it
that?
gets bigger.
Change velocity. She said acceleration. You just asked the question you just asked.
Oh, I guess I forgot that. Maybe there's something about redundancy in
It
education.
gets fast.
Maybe. Okay. So hopefully you are taking notes.
No.
Okay. But what Don tell us about acceleration? Acceleration is the change in velocity.
For the third time.
I know, it's good, isn't it? So acceleration is a change, going on number 4 here, Caleb. A change in velocity. Is it just a change in velocity?
Yeah.
No.
It's a change in velocity
Over time.
over time. What does over time mean? Over is a math term, or is a word for math term means what, Don? Divide. What's another math word that means divide?
Divide.
I'll give you a hint. Begins with a P. What? Per. And I have no problem spelling that one. Okay. So acceleration is a change in velocity per unit time.
Like PER or PER?
No, not like a cat purse. So
A cat purse?
whatever. Pers. Acceleration is a change in velocity per unit time. Now, what is the symbol for acceleration? Anybody remember?
No.
Isn't it A with the
It is A. Okay. The symbol is A with a
Line.
line. What does the line mean?
It means it's a vector.
Means it's a vector. Okay. So does direction matter?
Yes.
Direction matter. Does direction matter?
Yes.
Yes.
Okay. This is a vector. Okay. Do I need to show the video again?
Yeah.
Yeah.
Wait, there was a video?
Yeah, watch the video. It's from Despicable Me about vector.
Oh, I really. I do want to see
watch
that.
that movie?
Seriously?
All right. Yeah. For one little moment about, well, I guess there's a ton of physics in there. I will pull an article out there. I watched it a couple weeks ago. Great movie, by the way. If you haven't seen it.
Ralph?
No.
Or no, not you.
Wreck-It Ralph is a good movie.
Okay. So, guys, here's the symbol. The unit. Anybody know what the unit is? Well,
Meters
what's
per
the
second.
units on velocity?
Meters per second squared.
Meters per second, right?
I thought it was squared.
So it's meters per second per second,
Oh.
right?
Or squared.
So I can simplify this
And say second squared.
by saying meters per second squared.
Good job.
Now realize,
Okay.
when we write meters per second squared, that is the same as this. The reason why I wrote it this way is because if I talk about velocities and I say velocity are measured in meters per second, you guys can all tell me that's how far an object goes in a second, right? But then when I bring up meters per second squared and I say, well, what's that? I often get, it's just meters per second squared. But I say, well, what is that? What do these students tell me? Meters per second squared. They keep repeating that's meters per second squared over and over again. But what does that mean? They say that, good, they know the buzzword, but what does that mean? Okay, there we go again. We're stuck in a loop now.
The change.
You say acceleration, I say what's that? You say meters per second squared. I say what's that? You say acceleration. This will go over and over and over again until one of us gets really frustrated. It's usually you. Okay? But what is acceleration? What is it, Katrina?
Change in velocity.
A change in velocity
Over time.
per unit time. So acceleration, guys, is how much the velocity changes in a second. Okay? So if my acceleration is 2 meters per second squared, that means every second the velocity increases or decreases by how much? Okay. If my acceleration is 2 meters per second squared, that means every second the velocity increases or decreases by how much? 2 meters per second. Okay. Because with velocity, you guys have no problem saying if velocity is 2 meters per second, then the object goes 2 meters every second. Right? With acceleration, if the acceleration is 2 meters per second, that means, or 2 meters per second squared, sorry, that means every second the object's velocity increases by 2 meters per second. Right? So acceleration is the amount a velocity changes every second. I wish first hour, but I would have had the same questions you guys had. I think I would have done this example for them. I'll do it tomorrow. I do. Okay. So, let's say acceleration is 2 meters per second squared. We won't say positive. Okay. Positive 2 meters per second squared. I'm going to draw a particle. One particle. Okay. Now, if it's accelerating, what happens to the particles?
They get spaced out.
They get spaced out further, right? Okay. You guys see them? Yeah? What do our initial velocity be? Just throw a number out there. 4. Okay. Let's say V initial is 4. Okay. Let's say our time interval here is 1 second. Okay. Right? If our acceleration is 2 meters per second squared, how fast is it going after 1 second?
4 meters.
How fast?
4 meters.
It's 24 right now at 1 second.
Is it
Okay.
times?
After 1 second, how fast are we going?
So
No?
it's times
16.
6?
What did you say, Katrina?
6?
6.
So it's just plus 2?
It's plus 2.
Oh,
But it's
'Cause-
squared.
Every second. See, that's where kids get confused. Okay? They see that it's squared and they think we're multiplying or they think we're doing something different. Okay? But all acceleration is the meters per second per second. It's how much your velocity, how much your meters per second change per second. Okay? If velocity had a different unit like, I can't think of a unit right now. Speeds. No, that'd be confusing. Velocity, a different unit. Say the velocity's unit was shoes. Okay? Just throwing a word out there. Okay? If it said shoes here instead of meters per second, I think, and we didn't have the squared, I think we'd understand it better. Because we'd say we get 2 more shoes every second.
hey.
Okay, maybe that didn't work.
So we get 2
All right.
more meters every second.
Right, we get 2 more meters of velocity. We get 2 more meters of velocity every second. Does that make sense?
Yeah.
No. Okay, let's think about it this way. I'm going to draw a vector to represent this object's motion. Okay? This is the velocity vector. Okay? What happens here? What happens to the velocity vector here? It's increasing, right? Because we know the particles are getting further apart. So the velocity increased, right? Okay. So these vectors changed by, right? By this little bit right here. That's how much they changed by, right? Okay. So that little bit can be thought of as our, Skylar, stop talking.
Acceleration.
That little bit can be thought of as our acceleration, right? This is how much the speed changes every second. So when I draw, okay, we can drop the shoot thing. I think it's more confusing than it needs to be. All right. So if I were to go the next second, what's going to happen to this vector?
It's gonna get bigger.
How much longer is it going to be?
Whatever.
It's gonna be like.
It's going to be that little length
2.
longer. Okay.
2 meters.
Okay. See if I did a good job.
No. No.
Ah,
But that was
close enough.
line is thicker.
Okay, I'm sorry about that. Didn't know thickness Okay. Appropriate.
Oh, I mean like line.
Sure. All right. Now, let's put numbers to it now.
No.
Here, the velocity is 4, right? How much acceleration are we adding every second?
2.
2,
6.
right? So what's the velocity here?
6.
6. So after 1 second, the velocity is now increased by 2 meters per second. Oh, that's not meters per second.
No, that's
So here, after 1 more second, the velocity is now increased by how much?
2.
8.
Okay, increased by 2 more meters per second. The velocity here is 8 meters per second. Does that make sense, guys?
No.
Caleb, does that help?
Yes.
Okay. So when you're looking at acceleration, don't let the squared confuse you, George. The squared is just reminding me that it increases by meters per second every second. Okay? Think back to this right here. We have meters per second over seconds. Okay. Now, what might an equation be for acceleration?
What happened to our equations?
Hello.
They erased them and then didn't clean my board. Don't get it.
Why they? Why they?
I don't know why they erased them and didn't clean the board, but they
Why
didn't
did
clean
they
the
get
board.
those two?
No, I wrote those back up last hour. So you-
The janitor.
So
Yes.
it's probably one of those.
Okay.
So,
Guys, no, it's not one of those. Those are velocity and distance equations.
Then why did you?
All right, because I need them for class, and we'll get to that in a second.
Acceleration equals.
Okay, what does the definition tell us? A equals something good.
So v over second squared.
Okay, meters over, or meters per second over time, right? What's meters per second? Velocity, what's this?
Time.
Time. So it's something with velocity and time, correct?
change in velocity
Change in velocity
and change in time.
over change in time. Okay, which means I could write this as
So that's what the
Man.
V
Initial,
final minus
V initial,
V initial,
T final, T
Over-
initial.
T final minus T initial. Whoa, that looks like a slope equation. There's a little preview for where we're going with this.
Okay.
Instead of a position versus time graph, maybe a
Acceleration.
velocity versus time graph. Okay. Does this make sense?
Yeah.
Okay. Now when your book introduces this equation, they do this. So I will leave it like that for right now. Okay? And we gotta know that these V's are vectors. So we gotta put vectors on. Does that make sense, guys? Hey, that looks a lot like equation 3 up here, doesn't it?
no.
Well, Jameer, you're so observant. Looks a lot like equation 3, doesn't it? Now, equation 5 came from equation 3, didn't it? It did.
Oh, so now we're gonna have another one like that.
So, can anyone tell me what our equation 5 equivalent to this one is?
Wasn't it velocity?
I think you're on the right track.
tell us.
Okay, who could tell us? Me? Yeah, I can. But I want you to think of something. Okay. Or can anyone think of how I can take this equation and rewrite it like equation 5? By using algebra.
What does denote mean again?
Initial position.
No.
You know.
Okay. Can you think of a way I can rewrite it?
So why can't it just be di?
You can do it by algebra or by inspection. Well, some of you said 3 and 5 are similar. 3 looks like this. So our new version of 5 might look like this too.
Velocity equals AT.
So A equals.
Trying to go with it. Velocity equals
AT
AT.
plus.
D naught
Nope.
T.
If it was T.
V naught, yeah.
V naught. Right, what do you think V naught is?
A, T, and V.
Yeah. What do you think V naught is? What is it, Omar? Initial velocity, guys. There's some side conversation that need to stop. Okay, Rex, face forward. Guys, put your feet on the floor, please. Thank you. Okay, so here's our equation. Now I'm going to rewrite it close to this one so I don't lose all this board space. And it is like y equals. Once again, we're getting towards that velocity versus time graph. Okay. Now, does anybody have you here taken? Oh, you already said that. I already said that question. No one here is taking calculus. Okay. Or pre-calc. Now, in calculus, you learn that these changes in velocities and changes in times, those lead us to things called derivatives. Okay.
Wow.
Which is kind of like what we did over there with derivatives, with the tangent lines.
Yeah.
But what you'll notice there is that if I take the derivative of this function with respect to time, then we just get our acceleration. But I won't teach that to you now. It'll make sense later on when you're taking college physics. Yeah.
What?
College physics. You know, when you're in college taking calc-based physics. I did. You're gonna go out and spread the joys of physics in this cool world. Said cool, not cruel. All right. Any questions about those equations? No, we can't be done.
What?
I got like
Why'd
15
you try
minutes
to check
left.
a watch that's not yours?
because I usually have a watch. And you can see the tan line there. I just forgot it in my car.
All
All right. Are there any questions? Any questions? Anybody? Okay. You guys remember motion diagrams? Okay. Yes, you do.
We never learned about
Can you
Oh
explain
my
them,
goodness.
please? Can you explain them?
You guys have like a 24-hour rule when it comes to what I teach you. 24 hours later, we've all forgotten.
Oh, that.
That's what you
So-
That's like a Pokemon.
Here's some motion diagrams.
Just
Okay. Side conversations, although funny, they are very unneeded. Okay. So, which one is of an object that is stationary? Okay, the first one. Yeah.
Number 8.
Okay. This one is stationary. Right? I got this from your book. It's on like page 54 or something. Which one? Now, the following three are all showing, stop talking. Okay? Are all showing motion, right?
Yeah.
Right? Is it the same motion?
No.
No. Okay. Can someone tell me the difference between these motions?
C is
Raise your hand, please.
Okay, I got this.
Raise your hand. I'm going to talk the whole time. I don't know if I should let you.
I got it.
What do you think, Skylar?
Alright, B is constant, C is accelerating.
Okay, what was it?
Alright, B is constant, C is accelerating, and D is decelerating.
Okay. I don't like that word you used there at the end.
Well, it's negative accelerating.
I know it's negative. We didn't say positive direction. But you are correct,
Well,
though.
I mean, they're going that way, so I figured it's positive.
We can always
I'm
discuss.
assuming.
All right, but Skylar, you are correct. Okay. D is,
Well, that's B. That's
or B,
constant.
sorry.
It's
B
constant.
is
Constant.
constant. Okay. Skylar, sorry that my aversion of that word. I didn't want to taint your response. It was a good response, but I just don't like that word, deceleration. Just confusing, Caleb. Okay. So, what was this one?
Acceleration.
Okay, what's happening? Is it speeding up or slowing down?
Speeding up.
Speeding up, right? This one has an increasing speed. I like to use simple words. Okay.
So that's slowing down.
Slowing down, perfect.
Not decelerating.
Stop using that word.
What?
Decelerating. Terrible word.
Why?
Because it's redundant.
How's
All right,
it redundant?
We'll get to that later, not today.
It's bigger than a celery.
Okay. Perfect. Because you can accelerate in the opposite direction. That's what deceleration means. They add another word with a different prefix to confuse people. Use one word, just no positive and negative. We're all set. All right. So, stationary, constant. Okay. Stationary, constant, speeding up, slowing down. Does this make sense, guys?
Yeah.
Yeah. Okay, now, could we draw velocity vectors for B, C, and D?
You could for C and D.
We can draw them for all of them, though.
Really?
Right? Velocity vector is just the velocity at that moment. What do we know about all these velocity vectors for B? Are they
They're the same.
They're the same.
They're exactly the same. Perfect. So, velocity vector, velocity vector, oh, velocity vector.
You're not a good artist.
I know. I teach physics. So, those black arrows are all the velocity vectors, right? Now, in this one, what happens to the velocity vectors? They're slowly doing what now? Getting bigger. So we might have a small velocity, a larger velocity, right? And then a larger velocity,
Any question to that?
right? So those black ones are still my velocity vectors. Okay? What about the last one?
It's larger to smaller. Large, smaller. Smaller.
Guys, please stop side conversations. All right. Does that make sense, guys?
Yeah.
Okay. Now, Skylar used the word, and maybe that word was helpful for us all to kind of get a grip on the situation. That word decelerating. Ugh.
Hey, but
I hate that word.
you got-
But that word decelerating might help us think about our accelerations in these ones. He called this one accelerating, right? Anthony, Rex. And he called this one
Decelerating.
decelerating. So, slowing down, speeding up, right? Now, acceleration is our change in velocity. Is the acceleration increasing velocity here or decreasing it? Increasing or decreasing? I still can't tell. Who thinks it's increasing?
Is.
Who thinks it's decreasing? Okay,
I
good.
don't think it's
So, which way does the acceleration vector point?
that way.
To the right. So, the acceleration vector in this one is going to the right. I think I made that too long. Okay. Now you're probably like, why are you worried about the length? Well, the reason why, Jose, is because every time my velocity vector should be increasing by the same amount. So to go from here to here, the increase should be that. Okay? To go from here to here, the increase should be that. Does that make sense?
Yeah.
Okay. Now over here, which way is the acceleration vector point?
Left.
To the left.
Think about it.
Because in this one, Caleb, the speed is getting smaller, right?
But it's going the same way.
Doesn't matter. Because the speed is getting less. Okay? The vector, the acceleration, remember the acceleration is the change in velocity, right? Remember if we call it, like Skylar asserted earlier, to the right was positive, right? So we say to the right is positive. If my velocity is getting less, right? Am I adding a number to it or subtracting it? Subtracting it. So that means the vector has to be pointing in the other direction. Does that make sense? Yeah? Okay. So I'm going to leave those up there, but I'm going to take the picture away. Okay. So we still have our vector diagrams. And we're going to look at this. Acceleration and velocity. Okay. Acceleration and velocity. We'll leave those two up there. Okay. Now, what can we say about acceleration and velocity? When do we increase speed? Okay, don't use that word accelerate as just increasing, because accelerating can also mean decreasing. Okay. When do we increase speed? Okay, these vectors will be helpful down here. When we increase speed? When are the vectors getting bigger? Okay, we had the two situations right here, right? We had speeding up and slowing down.
Speeding up.
Right? When do we increase speed? Okay, thank you. When do we increase speed? Worried about acceleration and velocity, or the A vector and the V vector?
When it accelerates.
Okay, once again, thank you. Okay. When do I increase speed? Look at the arrows, guys. Omar, say it again.
When the arrow points to the right.
Which arrows?
The vector arrow.
So when the velocity arrows to the right and the acceleration is to the right. What if they were both to the left? Would we still increase speed?
Yep.
Yeah. So let's make it more general.
When the arrows are
Perfect! Okay, so objects increase speed. I know. Increase speed. When A and V, don't just say the arrows, be specific. Okay. When acceleration, no, point in the same direction. Objects increase speed when A and V points in the same direction.
Well, how do we know they're pointing?
Positive directions, negative directions. They're both pointing to the right.
Pointing.
Okay. So, example. Okay. Gotta get plenty of time still.
I don't think.
I know I said it was a minute left.
I don't think 6 minutes. Is
Hey, whoa. Let's say this is my initial velocity. Okay? Brand new marker. Let's say this is my acceleration. Right?
That looks so nice.
Okay? What is my final velocity going to look like? Okay, we're going to add together. Good. So these two added together will be my final velocity after 1 second. Okay? If we go 2 seconds, I'd have to add the acceleration twice and so on. But we'll get to that later. So I start my V initial. I think that's pretty good. Okay. And now what do I do with that acceleration?
you add it.
We add it using what method? Tip to tail. So there's my acceleration, right? So what's my final velocity look like?
It looks like a line.
Does that make sense?
Yeah.
Any questions? No? Okay. Now what about decreasing speed? Objects decrease speed when what?
When the velocity and the acceleration vectors are pointing in different directions.
Good. Not different directions. Because we'll get to one pointing up and one pointing right later on. Okay. Opposite. Perfect. Objects decrease speed when A and V points. Caleb. In opposite directions. Right? So objects decrease speed when A and V point in opposite directions. Scott, take a seat. Okay. So V and A. Let's say V initial, same V initial I had before. Okay. Now our acceleration is going to point which way? Instead of right, it's going to point left. Okay. So there's my acceleration now. To find my V final, what do I do with those two again?
Tip to tail.
Tip to tail. So we are adding them again, aren't we?
Yeah.
Okay. So what that equals
Is
is we still have V initial going this way.
mine.
Okay, subtracting that flips the sign on A. Got it. Okay. Remember the direction is negative, right? So I'm still adding them. And what happens to my final velocity?
It's
less.
small.
Okay. Does that make sense, guys? It is just like that.
Hold on.
Now, almost. That is 1 second, right?
Yeah.
This shows 1 second. If the top one, what? No, that's what the equation's for. Okay. If the top one kept going, okay, what would happen to the speed?
It would still increase.
It would keep increasing, right? Would it stop increasing? No. What about the bottom one?
It would start to decrease until it went.
Let me start going backwards. Perfect. Not zero, because it'll go through zero. It's just like this. When I throw a marker up in the air, it's experiencing gravity, right? It starts out with an upward velocity that's in the opposite direction as the downward acceleration, correct? Eventually the marker reaches a velocity of 0, and then what happens?
It
Comes down as fast.
It comes down, starts speeding up, right? And now the downward velocity is in the same direction as the acceleration, so it speeds up. Alright? So, when I throw it up, it's just like this bottom situation. After it reaches its point and passes through a 0 velocity, it's just like the top situation. So you can remember this just by throwing things up in the air. Okay? Alright, good job today, guys. A little talkative, but that's not too bad.
Hey, can I get the help with that after film?
No, because I got